Okay. All right, welcome. So I realize this is the last talk before lunch. It will be difficult, but I try to make it entertaining just a little bit. So let's first set the stage what we're doing. So this to us, and by us I mean our project and our team, we're focusing on this core idea. The core idea of SDV for us is to say that this is something for the OEM. This is not a customer end experience. The OEM, and I heard a quote of Jim Farley earlier, the OEM wants to be in charge of their software because they're tired of assembling hundreds of different black box control units. They want to be in charge of it. So they want to have a software platform. If you want to have a software platform that is consisting of many different pieces, well, then you're looking at a microprocessor. Maybe you're looking at Linux. You're not looking at microcontrollers anymore. It's too difficult to integrate hundreds of suppliers of software. So we believe that this is the next stage. So central compute with zones. You have seen this before. This is the big trend. Everybody agrees that this is the big trend. The reason why this is the big trend is because there's a microprocessor in the middle, and the zones surrounding it serve several purposes, but mainly collecting pins, collecting sensors, and collecting actuators. So this is the base setup. I think we all agree there are many challenges associated with this, organizational and technical. So let's speak about one single such challenge. That's real-time. I picked real-time because it's really not defined the same way by all people. So let's look at all of the vehicle software. Imagine you could, as an engineer, I like Venn diagrams, so let's start with the Venn diagram. This is all of software in the vehicle. This is the HLD part of the software. Safety. I think the circle is even too big. There are not many super safe functions in a vehicle. The ones we have are very, very important, but the amount of functions is not very high. This is the part of real-time functions. When you turn on the front lights in your car, you want them to turn on and not one after the other 5 seconds apart. So real-time is the most important feature. What is it? Well, real-time is not speed. That's what I hear all the time. Has nothing to do with speed. Has nothing to do with super femtosecond accuracy. This is not real-time. Real-time is connected, so the name itself is the real time, is the time we all share, the time that physics works. So when you look at your watch, all of our watches kind of work in the same way. So this is the real time. Translating real time into a maybe better word would be punctuality. So we're talking about punctual systems. Here are examples of punctual systems. On the top left, there's your alarm clock. Mine went off at 5:30 this morning. What's the tolerance of your alarm clock? Do you need it to go off at the microsecond when it turns 8 a.m.? Probably not. Is it still fine if it goes off like 5 seconds too late? Yeah. Is it fine if it goes off 5 seconds too early? Yeah. So real-time has a tolerance. Other examples, the next one is Outlook. Outlook is a real-time system. If it wasn't, you wouldn't use it to remind you that you have to go to the next meeting. Cell phones are real-time systems. When you record a video with a cell phone, this needs to be very reliably record your video in 30 frames a second. Needs to very reliably record audio. If you don't have stops and jitters and cracks in your audio stream, it needs to be a real-time recording. So real-time is all around us. Another example would be your birthday. You expect people to congratulate you for your birthday. Well, what's too late? Is a day too late too late? Probably not. Is half a year too late? Probably, yeah. And in our culture, congratulating too early is a mistake. So there are requirements associated with real time. And I've never seen those. How do they look like? This is how they should look like. On the x-axis, you have the time miss. 0 is you're right on time. On the y-axis, and I prefer here a log plot, is a histogram or a probability density function. Means if you do this a lot, how many samples, how many tries are right on time, how many are too late, which would be outside of the red line, and how many are too early, which would be left of the red line. And the red line is an upper bound. This is what you expect to be okay. Only expecting 0 is not going to fly. So real time is asking your function developers, how much can you tolerate? And he will answer 0. Well, that's not going to work. This is why this topic is such an important topic. What tolerance actually works? So I hear a lot of talk about hard real time. Mainly people say this to claim that their work is more important than others. My real time is hard, yours is soft. Look, this is a picture of somebody missed a traffic light. That's horrible. And most people define hard real time as if you miss the deadline, then something bad happens. That's not our definition. Look, we have requirements for deadline miss. Missing a requirement is never okay. So it makes 0 sense to have this. So here's the meaning. Hard real-time miss is safety critical. Well, what are you already planning on not fulfilling your requirements? Because that's not how we work. So if you fulfill requirements, the idea is, well, the difference is meaningless. The only thing is your requirements. And typically you would say in soft real-time system, I don't care if some samples are really late. Well, put that in your requirements. Those are mostly never written down. Another topic associated with real-time is determinism. Everybody needs to be deterministic. Well, also a bit difficult. Look, if you define determinism as 0 randomness and perfect reproducibility, this is possible. We're working with computers, right? This is not an issue. But don't expect to take a second measurement and to have that second measurement reproduce the first measurement perfectly. This is not how physics works. This is not how our sensors work, and this is not how the real world works. So asking perfect reproducibility, which by the way you can with microprocessors in Linux, you just have to record the whole kernel. But asking this from your own program while other programs are working on the same system and having only measurement from your program, well, I'm sorry, but that's asking a bit much. Do you really need this? Because if you take a second measurement, everything's out of the window anyway. So we say this is not, it's not a good definition. Here's a better definition. Relevant order is maintained. Yeah, you need to adhere to the timing constraints, of course, but order is maintained. One coming after the other. That's enough for determinism. This means now you can design your functions, your controllers for real time. You give them the jitter you expect, you give them the randomness you expect, and they should be able to design a controller that guarantees robustness. If you don't know how that is done, ask me. That's my core competence. So out of order calls are not permissible. This is the main determinism. This is also how Linux kernel developers would define that. Here's an example. On the left, this is what I had this morning. You have lanes merging in a traffic jam. There is a rule. You should have the zipper rule, like one car merges after the other. This is not followed perfectly. Sometimes you have nice people who let in 2, 3, 4, 5 cars, and sometimes you have not very nice people who do not let anyone in. This system is not deterministic because you cannot know the order of the cars coming out. It's impossible to determine what the orders of the cars coming out of the system are. So most of our systems are based on niceness. everything we do is niceness. So you can't say, oh, if you've waited a long time and you're not high priority, well, somebody will come and say, oh, you've waited a long time, come here, please. That's nice, and this is how our society works, and it works really well, but it's not deterministic. So we can't do that. We have to do the right side. Priority defines everything. That's how we need to define this. Here you have a true priority system, right? Everybody moves out of the way. You know exactly who comes out first, that guy. Here, I don't think I have time to speak about Linux schedulers, but real quick. Linux has several schedulers you can choose. And the normal one is niceness, and it's even called nice. So the nice term in the Linux scheduler that you're used to actually means nice. And it's not deterministic. It means everybody gets to run sometimes, you don't know when. The next is FIFO, it means first in, first out, so you have several threads that are on the same priority. So the next schedulers mean higher priority threads come first. What if you have several threads in the same priority? FIFA says first coming in goes out first. That's fully deterministic. Next one is round robin. Round robin means, oh, you have several threads that are equally important. You get a bit of time, you get a bit of time, you get a bit of time, and you get a bit of time. You don't know who will finish first. So if you have a program that relies on the order of execution, you have to maintain that order somehow through an additional logic. So round robin scheduler is not deterministic by itself. Neither is getDeadline. The getDeadline is, I like that one the most. We don't use it, we use FIFO. But similarly, getDeadline is not deterministic. But worst of all of them is standard Linux. So if you take an embedded pre-development board based on Linux and you put in the SD card and you think you can do real-time control with this, you are wrong. Any time measurement done with that piece is worthless. So here's the definition of real-time. Real-time basically means bounded response times and known priorities and known orders given by priorities. So here's an important takeaway. We typically do not make that requirement clear. And even controllers have jitter. And if we move to central computers with processors and true operating systems, even if it's QNX or some microkernel, we start to have to define the requirements on real time. And the digital filter designers and the control designers need to know how to deal with this. This is coming. So, here's an example from our test bench back there. Not today, but our best scenario, right? We're a bit slower because we're constantly evolving and testing different setups. We're doing 1 millisecond sample times, and 96%, if you can't read that, that says 96% of all samples are basically right on the money. That's a real-time configured Linux system. Already the next line is 1%. It's not 10%, it's 1%. So 1% of samples are slightly wrong. On the bottom, those are single samples out of 1 million. So a single sample is basically 50 microseconds late. That's what you can achieve with a real-time patched Linux kernel doing millisecond control. On a really weak hardware, by the way. This is not a powerful system. This is not a PC, this is our embedded hardware. So I need to know how much time I have left. This depends on if we talk about Linux. 5 minutes? So let's talk about Linux kernel if you want, because you need to configure your system. And the patch you need is the real-time patch or the preempt RT patch. So without the preempt RT patch, Linux is worthless. Absolutely worthless. in terms of real-time performance. So if you have Amazon's web service, that's fine, use it out of the box. But for millisecond or half millisecond sample times, not usable. But Linux is powerful. Before we would change to a different operating system, we would think long and hard about this, because any problem you have with Linux, somebody on Stack Overflow solved it, and because somebody on Stack Overflow solved it, ChatGPT knows how it works. Yeah? So ChatGPT is basically a powerful Stack Overflow search engine. And this is why we use Linux. It's very fast, all the tools are available. So here's a real-time patch. Don't worry, we will not go over all of these. But real-time patch essentially means whatever you think is holding back Linux as a real-time operating system has been solved. Every single detail. What has not been solved is an ALCD certification out of context. This is probably not going to happen anytime. Linux kernel is too big to do that, and it's changing too fast. But if you'll remember one of the first slides saying that, well, ALCD is basically 5% or 1% of all functions. Our opinion is leave those functions in the microcontrollers, move everything else. Because then we're very fast, very flexible, and real-time can be solved if you know how. Here is a final example of Linux without the real-time patch and with one. So what we do, we collect samples, 1 million samples, just to have a nice number. In reality, you would measure for a week. And the blue one means niceness, schedule a priority. And you see, we want a sample time of 1,000 microseconds, so a millisecond. And we get sample times up to 26 milliseconds. That's why I said Linux out of the box is worthless. Without the real-time patch, just configuring the kernel to be real-time, to be preemptive, we already dropped down to 350 microseconds too late. And these are old measurements, we're better now, right? We're constantly getting better. So the team back there, join us back there, we can show you how it's done. When we real-time patch this, in this old measurements, we have 11% deviation, maximum. This is what we need to do. And, well, I guess if I have time for questions, I welcome any.
Thank you very much, Dieter. Because we are in time, there is time for questions. Is there any question? If not, Dieter, you will be around.
Yeah. So we are 3 people on the right side of the backboard. We're showcasing in a very nice real-time example where you can feel real-time working. We have 4 motors controlled simultaneously in a millisecond. We can share everything with you because none of what we do is secret in any way. Come join us. We have very passionate, brilliant members who will explain to you whatever you want to know.
Thank you very much for that.